All right, so I did get a request this morning from Organic to go over page 50 and 56 in the study packet. Now, this page 50, this is a particularly hard problem. This is not typical of something you see on the exam. It's more meant to kind of be a challenge problem to get you to think a little bit harder about these types of problems. But the trick we're going to use to analyze this one is that we've got 4 peaks in the data. So we've got three possible potentially 3 structures that are being described here. Try a little bit harder there. So off the first bat, we know that we've got 4 peaks, which means we have to have 4 unique sources of hydrogen. So if we look at the first structure, we have 1, 2, 3, 4, 5 places for hydrogen. This and this are unique. This is unique, but these two are not. So way off the bat, I would discount this as a possibility. For this one, we've got 1, 2, 3, 4 sources of hydrogen, 5 sources with the OH group, and all 5 are unique. If we look at this one, we've got 1, 2, 3, 4, 5, 6, 7. So how did this one work out? I wonder what the key says. Key says this one. This seems like if you treat these two as equivalent, it works out. But they're not quite equivalent. So I'm not quite sure how I got that when I did the modeling. So my best guess as to how you approach this would be if you look at the signals, basically it's the only one that has enough groups left in it. So this one has too many hydrogens, this one has too many hydrogens, this is kind of the last one standing just by number of hydrogen positions. So 1, 2, 3, 4 positions. So I'll probably pull this problem off when I update the packets this semester. This is a bit on the super hard end. But yeah, the way this one worked out, it's the only one that can give you, assuming that you treat these two as equivalent, which I'm not quite seeing why they would be, that would give you the pentet. These would be your should be triplets. Yeah, I'm not quite sure, to be honest with you. And then page 56. Another ring problem. So this is going to go off of the number of unique carbon positions by symmetry. Is this carbon 13? Oh, thank goodness it's carbon 13. Okay, carbon 13 is a lot easier to do with rings. So the issue with doing the hydrogen with the rings is that, and I'm trying to read up more and more on this. I didn't do a lot of cyclic stuff when I was doing NMR. When we get to alkanes, we'll talk about axial and equatorial hydrogens. Those don't exist outside of a ring. So in a ring, we actually have unique hydrogen positions, even within the same carbon. There are unique hydrogens. Carbon is nice because we don't have these axial and equatorial positions. So what we're looking for this problem is the number of unique carbons by symmetry. So if we look at it, we've actually got two mirror planes in this one. So these are the same. These are the same. And these are the same carbons. So here we've got three signals. 1, 2, 3 signals. If you look at this one, we have 1, 2, 3 carbons that all look the same by rotation. These three look the same. And these three look the same. And if we look at this one, it's going to look exactly the same as this one. That cis-trans, like that's just a rotation plane. So we've got 3, 3, 3 peaks here. So next thing we need to look at are the relative ratios. So if you look at the relative ratios, these appear at a 4 to 2 to 2 ratio or 2 to 1 to 1 ratio. These appear all in a 1 to 1 to 1 ratio. And here again, we've got that 2 to 1 to 1 ratio. So if you look at the carbon-13 table, it says that the relative ratios are 2, 1, 1. So the only possibilities we have here are this one and this one in the carbon-13 because they're the ones that appear in the 2 to 1, 1 ratio. If the carbons appeared in a 1 to 1 to 1 ratio, we definitely have option B. So carbon-13 with rings, pretty straightforward. With the hydrogens, again, I need to start updating this notes. It's a lot more complicated because they're not, you don't have that confirmation they can't rotate. So we end up kind of getting, we actually start, even with on a carbon, we'll have 2 unique hydrogens. So we're going to stick away, especially for the exam, we're going to stick away from, move away from the cyclic examples. So those are all the questions I got in advance. I've got the chat menu up. If you've got any questions, please feel free to post something. I actually need to get a little work done if I can. So yeah, post a question if you got it. These are office hours. These are not lectures. These are not lessons. So please, if you got questions, ask them, but there's nothing prepared for this. All right, so just got to ask questions about reviewing J coupling. So what happens if we have two spin 1/2 nuclei? In this case, we typically talk about hydrogen. What will happen is that there is an interaction due to the spin states of the two hydrogens. So in a very simple case, we have a red and a blue hydrogen, and we will make here we'll just state that they have their own chemical shifts, with blue being higher than red. Now, the chemical shift is, the functional group is going to be what dictates the chemical shift, where the average of the signal sits. But with with spin 1/2 nuclei, particularly ones that are on adjacent atoms, they will actually couple. And this couple comes about from the fact that these hydrogens can exist in two spin states. So the blue can be in the 1/2 minus 1/2 spin state, and the red can be in the 1/2 minus 1/2 spin state. Now, for combinations where they reinforce, where they're the same, we end up getting more shielding, and in situations where they're on opposite signs, we get more de-shielding. And from this Punnett square, we end up getting equal 50-50 chance. So when we take a mole of molecules, when we take a large number of molecules, we get a statistical average. Now, for an individual molecule, yes, there is a selected quantum state for each hydrogen, so we only see one signal or the other. But with NMR, we're typically working with at least a few million molecules. So we do get the statistical average of basically an equal probability that they'll both have the same spin or opposite spins. So what happens to our NMR signal is that it splits. And for the simple one adjacent atom, it splits into two states. One where they have the same spins and one where they have the opposite spins. So we get both combinations. Now, as we start getting to more and more adjacent hydrogens, this splitting compounds itself. Now, the frequency, the number of ppms at which they split, depends on the nature of what's doing the splitting. So in this case, we have one hydrogen. It's going to have some J coupling constant 1 in terms of hertz, but that'll translate to a ppm. If we end up having a second hydrogen, we'll get a second split. Now, if these two hydrogens are equivalent, meaning that they can rotate and they look the same underneath the magnetic field, the split will be the same. And we'll end up getting within our, so if we look at the two hydrogens, if we look at these two hydrogens, they can exist in the same, with the same spins, with opposite spins, and then with the same spins but negative spins. So here we've got 4 possibilities. These two look the same because these two hydrogens have free rotation underneath the magnetic field. So this is our 1:2:1 ratio, and that's what we end up seeing here, is that there's a chance that both are in phase with the hydrogen, both are out of phase in the hydrogen, and then only one of them is in phase with the hydrogen. So we get some subsequent splitting and further splitting. So this is where J coupling comes from. Now, let's say we had a dissimilar hydrogen. It should be uploaded. I uploaded it yesterday. Let me check after the live stream, but it definitely should have been uploaded. Let's check. So on my end, when I downloaded it from the syllabus, there's definitely for the lab syllabus showing an A-B schedule. So you should be able to see that underneath the lab syllabus right now if you go to the getting started area, the syllabus area. All right, so what happens if we have a different hydrogen over here? Let me get a different color pen. Well, this is also going to split it, but it's not going to split by the same amount. So we've got these two hydrogens, and we've got the splitting pattern here due to the red. So let me draw this all in red. So we're only going to look here at this one hydrogen. So we get one split. To the first red hydrogen, and then a second split to the second hydrogen. So we got a J1, we'll do J red, J red, and J red. So this is an end result of these two hydrogens splitting the blue peak. Now the black hydrogen is also going to split, but it doesn't split it by the same coupling constant. So what's going to happen is that all of these peaks are going to get split by whatever the coupling constant is with the black hydrogen. And so when we look at our final NMR spectrum, we get a doublet of triplets. So this is where this doublet of triplets comes from, is that all these hydrogens adjacent to this one are splitting the hydrogen. It's just that ones on the same functional groups will split them by the same amount, assuming those two hydrogens are equivalent. And so what happens when we have hydrogens on adjacent ones is that we get our first set of splits followed by another set of splits due to this J coupling, and if we had another carbon out here, like a green carbon, it would further split it. So this is what gives rise to what are called multiplets. And multiplet is just a lazy way of saying that it's split it multiple times, so we have a lot of different J couplings. But that's J coupling in a nutshell. Now, the J coupling does not care how many hydrogens are on a given functional group. They only look at the ones around them. So when it comes to these two hydrogens, they only care that there's one adjacent hydrogen. So this will get split into a doublet. This will get split into a doublet. This gets split into a triplet of doublets, or a doublet of triplets. You're welcome. All right, if you've got questions, go ahead and post them. Don't think you really want to listen to me type, but I am here. All right. So questions on the exam will focus on, yes, we'll focus on your ability to predict where they should be in terms of their qualitative chemical shift. And also, so two things to consider in this room. Okay, so let's say I give you some spectrum. I give you a 13C spectrum and I give you a 1H NMR spectrum, and I ask you to predict which carbons or hydrogens correspond to which part of the spectrum. So when we talk about shielding and deshielding, this is all a relative sense. So the more shielded we are, we're usually talking about carbon with a lot of hydrogen. Because hydrogen is one of the few elements that in organic molecules that actually is less electronegative than carbon, so carbon ends up pulling up a lot of electron density. Now, there are exceptions to this. You'll talk about this as we start getting specific functional groups. Actually, surprisingly, alkenes, carbon-carbon double bonds, are less shielded, and also aromatic compounds are super deshielded. It's kind of weird. But generally speaking, the more hydrogens we have around our carbon, the more shielded we expect the compounds we expect the signal to be, so the more to the right we expect it. To get deshielded, you're talking about halogens, fluorine, bromine, chlorine, iodine, oxygen, sulfur, nitrogen. These are basically carbon bound to heteroatoms. And we'll talk about more specifically, there are reasons why alkenes are more deshielded, but generally speaking, what's going to shift you hardest is when you are dealing with halogens and oxygen bound to carbon. Now, this is just looking at the carbon NMR. There is also guilt by association. So the closer you are to this halogen, the more deshielded you're going to be. So if we had this compound here, we've got two sets of methyl groups, this one and this one. Relatively speaking, this is going to be more deshielded than this one, because this fluorine is adjacent to it. This will be true for both the carbons and the hydrogens. Now, it's probably not going to be a dramatic shift because they are pretty far away from that fluorine. But let's say we categorize these as A carbons and the B carbon. We definitely would expect to see the B down here and the A over here. Now, the other thing to keep in mind is that this is not the only information you have in a spectrum. You've actually got three pieces of information. For both carbon 13 and 1H NMR, you have the shift, and you also have the intensity, which will give you the relative number. So even though you see the spectrum, you're also going to be given the integrated areas of 1 and 2. So for the carbons here, we have 1, 2, 3, 4 additional carbons, all with area 1, 2, 3, and 4. So if you're asked to identify the A carbons, they're actually pretty easy because they're the only ones with an area of 2. And then as far as figuring out the B carbon, it's going to be sitting pretty far up here to the right. Your fluorine, let's call this B, C, D, E. We'll call the bound to fluorine the F carbon. We expect the F to be the most deshielded, so that one's the most obvious. And then as far as D and C go, E is definitely going to be more deshielded than D and C because they've got less hydrogen. So we got E, D, and C. But the thing is, there is a little bit of ambiguity in this. So don't assume on the test like you're going to be asked to like identify like oddly esoteric questions. These are not got you questions on an exam. So you're not likely to be asked, you know, identify, and you've got some like really strange, to give you an idea of a nightmare scenario. So you're given this weird hydra of a carbon compound, and you're asked to identify, make it, which of the methyl groups of these things corresponds to the carbon. And we would never give you that. That's absurd. No one could figure that out by hand. But definitely something like this. Could you identify the A group or the F carbons? That you should be really easily able to do. So when it comes to carbon 13, again, you're not going to get nitpicked on tiny details like, well, can you distinguish between this carbon and this carbon? No one can. Like, you can't do that by hand. But you can definitely figure out the extremes on the spectrum, and you can definitely say which you would expect to be more shielded or more deshielded. So there's the two pieces of information. The chemical shift, which is going to be strongly shifted by halogens. The intensity also helps you out. And then with the hydrogens, the other tip-off is the splitting pattern. So we got the J coupling. So qualitatively, I would expect the hydrogens to follow this pattern, B, A, C, D, E, F. But they may not, depending on how this material is interacting with the magnetic field. There might be slight shifts one way or the other. But the thing is that you can also predict that A here is going to be a doublet because of the E hydrogens. You know that the E hydrogen here is going to be a septet plus a doublet due to this adjacent hydrogen. The F here is going to be a doublet plus a triplet. D is going to be a doublet plus a triplet. C is going to be a triplet plus a quartet. And B here is going to be a triplet. So particularly with 1H and MR, the easiest way to tweeze them out is to actually look at the J coupling and figuring out, okay, this peak is, which ones do we have listed? It's a doublet and a triplet. So it's going to be down to F and D, but you're going to see on the spectrum all of this. So the F hydrogens here are going to be more D-shielded than the D hydrogens. So you should see two doublets and triplets. The one that's further down is the one that's closest to the halogen. If you see a doublet, it's really apparent that you're dealing with A here because it's the only thing in this spectrum that has a doublet. You can also do process of elimination. Some things you can just look at and automatically tell. You know, B is going to be a triplet, A is going to be a doublet. If you're not being asked to find a doublet or triplet, go ahead and scratch those off. Now you start narrowing down the possibilities. So this is what I mean by predicting the spectrum is much more useful than going the opposite way, taking the spectrum and predicting the molecule. It's easy to do process of elimination. It's easy to start guessing as to what features you would expect to see in there and comparing that to the image. So that's more what you need to be able to do is that off the bat here, without having to draw any of the spectrum, I can tell you what the splitting patterns are going to be. And if asked to identify the D carbon or the C carbon inside the molecule, D carbon or C carbon in the spectrum, for the hydrogen, the easiest thing to do is start going off the splitting patterns and figuring it out that way. But again, like you're not going to be given some weirdly esoteric example like the hydra I drew before, like, okay, a whole bunch of them are giving these doublet and triplet patterns. Which one in particular corresponds to this? Well, that's nitpicking, right? Like there's a lot of nuances when things start getting that far away from the halogen. There's a lot of nuances when you see a lot of similarities in the molecules. You're not going to be given ambiguous cases. Like it's going to be really apparent if you understand J coupling, if you understand chemical shifts and relative intensities, how to figure out which signal corresponds to which part of the molecule. All right, so that's it for the live stream today. Again, if you ever have questions, please feel free to email in advance. Enjoy your long weekend. There is no live stream Monday because we are off, and I will see you all Tuesday.